Okay. Okay, we're going to get started here today. I'd like to begin by apologizing again about the Tuesday lab issue. The lab was posted sort of in the middle, I think, of the second lab, and that was my bad. So please excuse the oversight on my part, and hopefully the extra time afforded by the lack of class and the fact that the lab this week is a little bit shorter and you have a little bit more time with it will help you make up for that. But again, I apologize for the inconvenience caused. So today's lecture is largely shaped by the content of that lab. And specifically on the lab, there's a requirement that you work with an artifact called a makefile. And I want to explain what these makefiles are, the role they play within the software development process, and why they can save you a lot of time, a lot of risk of error, and generally serve as sort of key pieces within the software development process. And hopefully we'll make this a little bit interactive so we can see an example of how a makefile works in action here in the course of the session. I have, to facilitate your exploration of this material, I've placed a set of makefiles online on the course Moodle site just prior to this. I had trouble doing it earlier because of some network problems, but I was able to do it from this room just before starting up here. So if anyone's interested in following, if you go to the Moodle site and you go to the section that's called, I think, Example Makefiles, you'll find a bunch of makefiles, and in this case, you'll find source code in which, to which they refer and whose builds they're being used to sort of facilitate. Okay, so you can find that. You can also find these slides online right now as well. Okay, so all of you, if you've reached this point within your CS training, CS education, you will have engaged in a process known as a build. What is a build? When we talk about building a system. Okay, yeah, so that's some of the most critical pieces of the process is turning the code, which we may have specified in a so-called high-level language, a language like Java, C#, or even in a low-level language, a language like C or assembly language. It'll turn that into something the computer can run, right? And what's the tool that actually undertakes the key steps to turn that specification that we can read into something the computer can execute? It's called a compiler. Well, compiler. More generically, though, and so compilation, the process of using the compiler, is often the central part, or the most obvious part of a software build. Okay. We talk about when we modify a program, when we build it, perhaps the most fundamental, the most far-reaching of the set of things that we do is we compile. We get it so the computer can execute it. Among other things, that lets us run it, but it also enables a broad set of tests to come. And a build, more generically, includes compilation, but it often includes a set of processes, a set of actions that transcend merely compilation. So if we think of a build, we think of building our software. Compilation may be in that. Often, that's the first step, but not always. We'll see here today, for example, that we might do a build that will start by cleaning the slate, so to speak. So we could say, for example, make minus f makefile. I'll do it with the latest makefile, and we could say clean, and that will actually go and clean things up. So let me set the lighting here. There we go. So here I might do a build where the main purpose is actually to clean things up before another step where I recreate them, for example. And more generically, that might be done before the stages of compilation. So there might be some cleanup done here. Another thing that might happen is that certain components of the code might have to be built up. You know, normally you think of yourself as writing code, but a lot of code that's out there these days is automatically produced, quite a bit. So we might, you know, generate some code up here or something along those lines. We might end up going and fetching things from different sites, which are different resources, etc. So there might be some steps up here, so you know, clean up, etc. Then there might be a compilation. Sometimes, often this is the first process. And then we might do something with the results of the compilation. One thing we might do is simply test it ourselves, but what other things might we do besides manual testing? We might do some automated tests. So we run suites of tests that sort of exercise the program and make sure that everything is working properly. So automated tests, or a substantive component of what might happen. In other systems, ladies and gentlemen, you might get check-ins, or more generally, you might get deployment, I should say, deployment to test machines elsewhere. So you built this system, and now you want to distribute it to a bunch of people so that they can test it effectively. So you might deploy it, goes out and puts around. There might be a set of other processes associated there with monitoring the results of the build, the size of it, perhaps sending emails. And this whole thing would be called sort of the build process. So talk about a build process. The key piece, often the most central, sometimes the main one, is compilation. But it's not the only one. There's often all these other things that we want to have going on. And if you look at the later makefiles, there's 6 makefiles, I think, that I put up on Moodle. The later ones of them include processes, for example, that might involve testing. So when you build your system, it goes and recreates tests, for example. So here we have a system where there's a bunch of things going on within a given build. And often it's a quite complicated process. Now, in compilation itself, there's actually a lot of things going on. We might commonly talk about compiling a program, so we write, you know, G++, you know, foo.cc or something like that. But within that actual, you know, that step, something we consider a single step, there's often several processes going on. Typically, there are. You can use command line options to suppress them. But one of them is a preprocessor. What does a preprocessor do? What does it handle? What sort of things? Macros? Yeah, macros. So a preprocessor would deal with things like pound defines, making sense of pound defines. Remember that pound define max to be sub A of A and B to be some expression. Then when we use max in our code, it actually gets expanded into whatever this thing is here. It's expanded into it. Another thing is pound includes. Where you see these pound signs, that's a sure sign that preprocessor is getting involved in C. So pound include, you know, might be some libraries, io.h, something like that. And here, the preprocessor is actually going to take care of getting the requisite header file here, going and looking it up, fetching it, putting it into our program. so, ladies and gentlemen, what emerges from the preprocessor, if we can sort of represent this, we have our maybe .c file or .cc, depending on it. What emerges from the preprocessor is, so this is the preprocessor phase, is actually a set of source code that's based on ours, but these things have been expanded in it. So max has disappeared, it's been replaced by stuff. Pound included disappeared, it's been replaced by the contents of stdio.h and so on. Okay? Now, these things don't really have a good name, but sometimes the name of .i files, you don't really see them most of the time unless you request it, unless you do gcc -e or -et to sort of look at sort of what's there. And it's really this then that gets compiled. So it's really this that then this is like the pure C language, so to speak. It doesn't have pound includes and stuff, which are really preprocessor based. And this undergoes compilation in the strictest sense of the word. And it gets turned into, for example, a .o file on Linux. On Windows, it would be called a what? .obj file. And in both cases, the O's, obj, they stand for object file. It's called an object file. And then what happens, folks? What's the next stage? So can we run a .o file? You need to put them together, because typically this is not something which can be run in a standalone fashion. It depends on other things. What other things might this depend on? A .o file, what things might it depend on?
Libraries?
Libraries, yeah. So it might depend on the sign function, depend on some command in Windows to pop up a dialog box or whatever. So, this is your code in it, the contents of this .c file, but typically, to allow it to be run, you need to so-called link it with other things. You need to sort of have its, another word we might use is its dependencies fulfilled. It's going to depend on some things. It depends on the sign function. So it has to be linked in with the sign library. And there's several different ways of doing that. Dynamically linked libraries, statically linked libraries, which have to do with sort of, is the actual code for signs stuck into the results, or is it simply referenced in a place it can get it from elsewhere? But this might give, on Windows, for example, exe, a common default name for the executable. On Linux is a.out, or whatever name you want to give your output. So this is called linking, okay? The linking process. I'm particularly tailoring this to C and C++, because that's what we're using in this class. How would it be different, ladies and gentlemen, if you were using Java? You folks are using Java 270? Yeah, okay. So how is this different if you're using Java? So suppose I have a .java file here. So .java. So that's my file. How is this different? Do I get a .o file out of a Java? What do I get? .class file. Sometimes you can ask for a .jar file. It bundles together onto .class file. So the pre-processing step is absent. You don't have this kind of schizophrenic system in Java where you have sort of this bunch of stuff that's handled by the preprocessor. Pound defines, macros, that sort of stuff. Pound includes. And then you have the rest in sort of real Java. You don't have that in Java. You have sort of a single consistent language. So there you go from Java to a .class file, and you would then link it up to other files, say .jar files, and you would create an executable Java program or executable jar, or any number of different sort of outputs that you could have that would be executable, for example. Could be an applet that's produced or what have you. So here, the pre-processing stage is absent. Here, and this has been bit of a distinction that's a bit subtle right now, but fundamentally the class file can run on many machines, whereas this is typically specific to your type of machine. This is close to the metal, as we say. It's designed to run on your specific machine, whereas this .class file is a generic thing that's designed to run on something called the Java virtual machine. Okay. So we have this basic process across languages where there's sort of a compilation and a linking process, and it differs as to whether the compilation kind of includes this pre-processing step. Okay, so this is a staged process. So in C, we have this preprocessor, compiler, and then a linker. And the linker deals with both libraries, like things that are signed, things that are winner, things that somebody else wrote, as well as modules you might have created to divide the program up into nice pieces, to nice sort of modular units that you can use across multiple projects, perhaps for some of them. Some of them might be a really nifty tool you write up and it can be used in many different projects. And then later, it turns out that the linker weaves in a lot of code here for so-called static library modules, but then there's ones that it'll actually leave truly getting their code until the program runs. And these are called dynamically linked libraries, or dynamic libraries. So I don't know, how many people here in Windows have seen .dll files? Those are dynamic linked libraries. And the vast majority of things that you link to in Windows will be dynamic libraries. Why? Because then you don't have to go take all the library code and put it into every program in turn. You get one place to go where they can be shared. They can all refer to a single dynamic link library. That's the theory of it. Turns out the devil's in the details, and there was a phenomenon known as DLL hell that's still found because sometimes you depend on different versions of that dynamic link library, and what if the version is overwritten? Okay. Now, the issue here, folks, becomes more textured. So that's the basic process, and it becomes more involved the more and more dependencies you have. So very commonly, for example, our code will depend on libraries, things that provide the basic functions our programs need to operate, or things that we've gotten that do useful stuff for us, that allow us to parse HTML code or what have you. Okay. So if we use libraries, and you saw this earlier in a lab, for example, and we try to naively compile a program here, this .cc program here, we might get an indication, for example, that it doesn't know where to go for square root. And we have to tell it, hey, go to the math library to find that square root. That's what this -lm means. It says, hey, when you're going and you're compiling this program, and actually here we're compiling and linking sort of in the same step. When you're doing that, right here, when you're trying to turn this into a runnable program, first compiling it, first preprocessor, compiling and linking, you got to pay attention to the fact that this is using things in the math library. So this -lm is an indication of where to look. It looks for libm as it's located somewhere. So it looks for this guy here, okay, to go find the code. And it knows to do that because we said -lm, and so it goes there and it finds square root just fine, and it's a happy camper. Okay? Okay, so when we depend on standard built-in libraries, this works great. But what if we depend on code written by ourselves in other modules? What if we depend on code written by our coworkers? What do we do? What do we do? How are we going to sort of link that in? Every time are we going to type out G++, the name of our program? Are we just going to do up arrow so we can go back to it and bash or what have you? Are we going to type in the command line to link it every time? Should we just create batch files that do this, scripts that do this? Well, it turns out it gets messy if you don't have a principled way to deal with it. So We're going to be going through the next few lectures in an example called the n-queens example, which is an example of test-driven development we'll be building up. But in this case, I want to jump forward a little bit and talk about a situation which is shown on the Moodle site, where we in general will have a single program here, the n-queens program, but it consists, ladies and gentlemen, of multiple modules. You may have remembered in a previous lecture I talked about the principle of separation of concerns. Can anyone recount for me, describe for me what that principle exhorts us to do? What does that principle sort of guide us to do? We say we want to achieve separation of concerns within a program. Okay, so there's some specialization involved, that's right. So we may have certain regions of the program that are more specialized for certain things. Perhaps it comes across most strongly if I say that, among other things, it means our program shouldn't just be a hairball. It shouldn't just be this tangled mess where everything sort of talks to everything else and it's just all mixed together. We have segmented sort of purposes. I mean, in your house at home, you have different rooms for different purposes, right? So you have a bedroom, you have a closet, perhaps a mudroom, you have a washer, you have perhaps a storage area, laundry area, and when we have a building of some sort, we kind of organize things so that we know where to go for certain types of resources, right? And it's rather convenient to not have to worry that our muddy boots are going to be mixed with our bed, for example. It's kind of a desirable thing. And it's kind of nice to know that our the oil that we use to lubricate our bike chain isn't mixed in with our food, that we're going to be eating and so on. So we have separation of concerns. We separate things out into different specialized areas. And we do that because different people can work in those different areas, because we know where to go to find certain things, because we have clarity of what we're dealing with when we're in a certain area, and we can organize it in a very well-defined way. So it's similar with that with software programs. So here we have an overall goal. So the goal of this program is to print out chessboards of a certain specified size, n by n, where we imagine that we indicate where queens from chess could be placed such that they can't capture each other. So, people here familiar with chess? Okay, so who can tell me what moves a queen can make in chess? Okay, good. So, if you have a queen here, the queen can move sort of along this axis, and then along the 45 degree lines, right? You can move sort of those directions. And so the goal of this program is to identify chessboards, legal chess configurations of size n by n, where there's n queens on them, and none of the queens can capture the other. It sort of prints out renditions of these chessboards. And you can run it if you want from the Moodle site, and you can run it from your lab. So this program, which accomplishes the single goal, does so by a separation of concerns. So it sort of partitions off certain types of concerns into different pieces. So there's a set of pieces that have to do with sort of characterizing the state of the board, certain that have to do more with problem solving, and certain that have to do with testing the appropriate areas of the program. And then there's sort of one thing that coordinates the moment, sort of a controller that calls off to this, calls off to that, etc. Okay? So here we have, well, I don't want to go into the details of this right now. That's not the point of this lecture. What I want to communicate is that typically, ladies and gentlemen, if you're going to be creating C programs, You're going to be creating Java programs. You're going to be creating websites. You take case after case. The thing that you're going to create will be composed of several pieces. Be composed of many pieces. Just like, normally a home will have several different rooms in it. You can have a home with just a single room, bachelor's pad or something like that. I won't speculate, but where everything's sort of in a single room. And you could have a program where there's just one file. We've done that before. foo.c. But generally speaking, we have these programs divided into pieces. So here we have a bunch of pieces. And I talked with you about the purposes of the .h files and the C files, corresponding C files before. Okay? So here are these C files and some header files in which they depend. So, if we're to go, for example, over here, and we, oh, it aborted. Let's go back and try this again. So we could go take a look, for example, at particular things here. Makefile. So we could take a look at solver.h, solver.h, and we'll find a bunch of things it depends on and a bunch of signatures of functions together with contracts. And I apologize for the coloration here, but broadly what you see is functions, for example, that it seems is block that returns a Boolean, and some description, some contract that describes what it expects as arguments and what it returns. What its job is in life, the what of it. Now, that's in a .h file. That's the interface file. That's what other things would include to use these functions. That's what they would need to know to use it, this sort of stuff, the what it accomplishes. And then there's the actual implementation, right? Solver.cc, where these things are actually implemented. Here's, for example, the isBlocked routine here that actually implements that interface, okay? So fair enough, we have these different pieces of a program, and as you can see, there's a fair number of files here. And generally speaking, if we have a program of any size, there'll be many such files, maybe 20. I routinely work with projects with dozens of these files at the same time. There are dozens of them, divided up into dozens of pieces. So here we have these .h files, which define the interfaces, and .cc files, which define the implementation, and we can go and we can compile these sort of things and run them. The question is, how do we manage the compilation of all these pieces? Okay, so all of these things are needed. How are we going to, suppose we modify one thing here. Suppose we modify solve.h. What thing should we recompile? Well, you tell me. What thing should we recompile? I changed solve.h. I realized that there was a typo in there. Or maybe I want to go and change it so that we insert a new type there. What has to be recompiled? What has to be changed? Okay. Good. Good. You'd have to, because this probably ends up using solve.h. How do we modify state.h? Okay, also it turns out solve.cc uses it turns out. Now, but this is exactly the point. There might not be perfect knowledge on your part about what uses what. It's easy to forget. At one point, it may be that solve.cc didn't use state.h, now it does. And the question is, okay, if we go and we frog something, if we go and we change it, so I change, for example, state.h here, to modify something here, perhaps to insert another element of this structure, to change this maximum count of queens that are supported. The question is, what do I have to go and recompile? And you know, this is something which is solver.cc. Is something which may not be obvious. We could go figure it out. We could go, for example, say, okay, this includes solver.h. Does solver.h depend on state.h? But generally, it's a pain to sort of have to remember this or have to go figure it out every time. So the idea here is to try to make this process easier, to try to automate it, to try to make it so it's not a burden on you, so it's not just one more big distraction. So you can really focus on it. And this problem is especially acute when you're working with someone else's code, because you're going to have to spend a long time to figure out what has to be compiled. Let's suppose that I modified something, say state.h, and suppose it turned out that solve.cc did in fact depend on it, but I didn't compile it. What would be the consequence of that? What would be the consequence of omitting compilation when it should have occurred?
Depends on the change.
Okay. Could that be problematic? In a big way, ladies and gentlemen. Now we can have a single program where state.cc thinks the state has this information in it, and solve.cc is using states, but it's using the old version of states, the version that didn't have that information. And they're not going to talk with each other properly. They're not going to understand how to talk. It's almost as if, you know, the bus STC or the bus here in town for Click and Go had one schedule, and you were operating on an old schedule. And you go out and you wait for the bus for 45 minutes, and it doesn't come. It shows it freezing. And you know, we've had just a big waste of time. It can lead to errors in the code because of misunderstandings. Well, I think state means this. He thinks state means that. I give him a state, and it means something different to him than I meant it to mean. So in general, if you don't have compilation, if solve.cc actually did depend on state.h, maybe through solve.h, and we didn't compile it, we could get a program with bugs in it. These wouldn't be true bugs. Let's put it this way. These wouldn't be bugs that are programmer mistakes in the code. These are bugs because we got them using different versions of the software. And that can drive you just totally nuts. You go and you go track down a bug, spend a day tracking this thing down, and it turns out not to be a real bug. It was just because you forgot to recompile this. That's not a pleasant realization, but it's a real one. And as I said, it may be that solve.cc depends on state.h, but it won't be obvious because it depends on solve.h, and maybe solve.h includes state.h. And without going and tracking things down, we're just going to be really confusing. So how do we stop this madness, okay? How do we stop it so we don't have to type things in, we don't have to keep in mind what depends on what, so that it takes care of all the stages here, so that perhaps we can tell it, hey, build everything from scratch because we've changed a bunch of things, or what have you, or maybe we put it on a new machine and nothing's there. So the idea here is to have software do it. Look, software is good at bookkeeping. We're not particularly great at bookkeeping, but software is really great. It can be very consistent about recognizing what needs to be recompiled. So let's get the computer to do this job so that we don't have to. So that we can focus on higher level, more subtle things. Things that aren't just sort of rudiments of details. Okay? So what's needed for this? Well, we need some way of specifying both the components in our program, some way in which one depends on the other, like this .c file depends on this other .h file, and maybe that .h file depends on these other .h files, right? And then we need some way of sort of saying, okay, if one of these things changes, if any doing, recreating your component of it. So if that .c file changes, maybe we have to recreate the .o file, for example, or the .object file, right? And then maybe if that changes, then we have to go recreate the executable file. So if we change that C file, all that gets done for us. It goes and creates the .o, and it goes and creates the executable file. Maybe we change the .h file, and it should ripple through, and okay, because the .h file changed, we know this C file changed, so that C file changed. That C file has to be recompiled, and that produces an .o file, and that gets turned into an executable. And of course, ladies and gentlemen, that might not be the end. And then it may say, well, now that the executable has been produced, I might have to do what? Remember, in the first few minutes of the lecture, I said it's not just compilation. That executable file is now ready. What might I do with it? I might test using it. I might deploy it to multiple systems, for example. I might document it, check it into a repository, all sorts of things that might be done after that. We want the software to automatically keep track of this, not us. Why burden us with it? We have better things to do with our time. So the idea here is to get it to be intelligent about compiling, to do just the amount of work that's required in a given circumstance. Don't go recompiling code willy-nilly. Do it when it really needs to be recompiled as something that it depends on its change. And we'd like to do it in a fairly lightweight way. Okay? So the good news is that there are a wide variety of tools out there that help us go through this process. And many of those in the room, perhaps most of those in the room, perhaps even all of those in the room, will have used integrated development environments, IDEs. These are things like Eclipse, Visual Studio, Code Warrior, Xcode, etc. These sort of systems help manage your projects, help recognize what depends on what, and take care of building the system, right? So that's one option. The problem is, ladies and gentlemen, especially when you're learning early on, it's not obvious what's going on beneath the hood there. It automatically takes care of it. You don't know what it's taking care of. And you might say, well, what's the matter with that? It's just, I don't know what's going on in the carburetor. Fuel injection system of my car. Why do I have to? Well, there's two reasons. One thing is that if you don't know what it's doing, you might not realize its vulnerabilities to mistakes. Sometimes you might not know it has to recompile something. You know it. You know this thing has changed, but for whatever reason, it's not going to detect it. And you might have to kind of nudge it in some way. A second reason you might really care about this is because those mechanisms and IDEs are often not as flexible as you really like them to be. There might be certain types of things they're set up to do, and other types of things they just can't do. Maybe they can't go deploy code elsewhere. Maybe they can't run certain types of tests except in these environments. So there's more flexible mechanisms you can use, and I've listed three of them here: shell scripts, Makefiles, and amps. We're going to be talking about Makefiles because they're sort of front and center for C development. And this course does help try to prepare people for classes like 214, where these are a major part of the focus of attention day to day. However, I will note that if you're operating in the Java world, and I look forward in another year and a quarter to welcoming many of you to one of my classes where we use, say, 371. We're doing large development, often much of it in C# or Java, sometimes other languages. And tools like Ant are really useful. These are tools for keeping track of these dependencies that are, frankly, cleaner than Makefiles. Makefiles are sort of rough and ready. They are old and venerable technology. They are not the most user-friendly sort of things, but they are incredibly flexible. It turns out Ant has many of those virtues while still being much, much prettier to work with, much clearer. Okay, so why are we working with Makefiles? Well, they are a standard across the Unix platform. programs. A lot of the things you'll download that have to be compiled under Unix will have Makefiles associated with them. They actually knit together the Windows world and the Unix world, including Mac OS and they're very, very general and powerful. And the fundamental ideas behind them lie behind most of the IDE implementation. So if you understand what a Makefile is doing, you kind of get to understand quickly what an IDE is doing. And most of the time, you may be able to depend on that. Most of the time, I depend on that. Okay, so we talk about Makefiles. Why that name? Well, they make our program. They do the build for us. But at an even more prosaic level, they work with a program called Make. It's actually another program called Nmake. It's quite similar, but has some differences. Figures out what to do before doing any of it, for example, is one option. So there's a long and established sort of set of literature on Make, and one of the better resources is this one in the GNU project, which will refer you to some of the details with Make. Make can be a little bit arcane, but we're not going to be getting into that arcana here in any detail. So we're going to be talking about the very, very basics of Make. And you should realize that there's lots and lots of detail for those interested in going out and exploring all of it visually. Okay, so a few basic concepts associated with these Makefiles. The first of them is a target. Okay? So we have something perhaps that we want to be able to use. Maybe it's our entire system. Maybe it's a particular file in the system, a .o file, or a specific .exe or specific executable in Unix. Remember, our system may have many executables associated with it. There might be one that's the install program, one that's the program to actually run our system, another is a program to read corrupt files for our system. There might be several executables that come within your project. You might be interested in one of them, or you might be interested in just saying make all of them at once. Okay, so if I'm over here, for example, in these working with these components here, I might say, for example, make -f makefile 6. So I specify which makefile to use, and I want to say make everything, and it goes and it automatically produces all the requisite pieces. So it says, okay, to make all, and we'll see where this is defined, I need to go systematically make a set of pieces. I need to make this Queens program, and to make Queens depends on three things. It depends on queens.cc, state.cc, and solver.cc. Excuse me, I should be more careful. Queens depends on the corresponding .object files of those, and so I have to go compile each of those. And then it also knows, okay, I probably want to produce the testing components. Okay, so here I have a target. Alternatively, maybe what I do is I can go clean these away, and maybe I say I want to produce actually Queens specifically. And there, I'm going to be doing whatever's work needed to produce this Queens program specifically. Not Queens and testing for Queens, and testing for things. It's just producing Queens itself, okay? So I have a target. I have some component that has to be brought up to date. It could be a binary file. It could be a file of produced code or what have you. And then I have a set of dependencies, things that this depends on which this depends. So the Queens program, ladies and gentlemen, depends on a set of object files. So if I go here and I look at, for example, makefile 1, I can go see, for example, that here, the Queens program here depends on 3.o files, 3 of these object files, solver.o, state.o, and queens.o. Each of those, in turn, depends on certain resources. Here, state.o depends on state.cc and state.h. solver.o depends on solver.cc and solver.h. Okay, so there's a dependency. Finally, there's an action associated with it. Okay, if any of the dependencies has been updated more recently, as measured through its timestamp, then the target, then we got to make the target. We got to produce the target. It's a sign that the target is out of date. These things it depends on, a .h file, for example. Maybe we have a .o file. Maybe we want to make queens, and it depends on solver.o, and solver.o depends on solver.cc. Maybe we modified solver.cc. Hey, we've got to go, if we want to produce queens, we have to first check, okay, is solver.o up to date? And solver.o up to date will say, well, is solver.cc been modified since I've been produced? The answer is yes, so I've got to be recreated. I've got to be remade. I've got to be rebuilt. So ladies and gentlemen, here if I'm interested in queens, it depends on solver.o. Solver.o depends on these things. And when it considers this, it'll say, is solver.cc updated later than solver.o? If the answer is yes, it undertakes this action. It'll say, is solver.h more recently updated than solver.o? If so, undertake this action. Okay? Once it undertakes this action, solver.o gets updated, and then queens will get updated because solver.o is more recent than queens. So it examines this recursively. It examines, okay, is queens out of date? Well, that depends if solver.o is out of date. Is solver.o out of date? That depends on the relative times at which this has been updated relative to solver.o and that this has been updated relative to solver.o. Let me ask you this, folks. Suppose that queens depends on these things here and it can't even find solver.o. What do you think happens then? Yeah. So if it can't even find it, it's time to make the donuts. It's time to run that command so that solver.o gets produced. So if solver.o here is out of date, it'll run this command. If these two, solver.cc and solver.h, have been updated since solver.o, then it will update, it will run this command here. Or if solver.o doesn't exist, it will run that command. Okay? So here we have these rules that specify an associated dependency and some action when that dependency indicates the target here is out of date. This indicate that we have a target which is older, which is obsolete. It's older than the things it depends on. This will be run, or if the target doesn't exist, this will be run. Okay? So this is a particularly simple version of a makefile. You'll notice, by the way, one or two things. It pains me to talk about this. I feel a measure of shame speaking to you about the burden laid by my generation on you. And we're not talking here about CO2 levels or global warming. We're talking in this case about the focus here is about the fact that Make is notoriously sensitive to white space, ladies and gentlemen. This is a tab here, and it will be at your peril if you replace it by spaces, which might be totally invisible, and that's why they're so deadly. So the basic syntax is a target list, a dependency list, a tab, and then an action. Okay. There should be no white space at the start of the rule. Comment lines begin with the hash character. And there are versions of white space that allow arbitrary, but don't push your luck because some are extremely dependent on only a tab being there. Okay, so we saw this sort of example. We might have this depending on that, and some rule associated with it. Okay, so multiple rules. If you include them in your file, they should be separated by at least one blank line. And as I noted, if the dependency is a target, in other words, if Queens depends on something here, solver.o, that itself is a target later in this program, later in this makefile, the rules get applied recursively, okay? So it'll get applied first to solver to figure out if Queens is out of date. First we figure out if solver.o is out of date. To figure out if solver.o, Queens is updated, we figure out if solver.o, we're going to have to ask, has it been updated more recently than Queens? To do that, we first figure out if solver.o is out of date, and to do that, we use this command. We could have solver.h, for example, depend on something else if it's automatically produced. Okay, and it's considered good practice to put the sort of default rule up front here. Sort of have it go from most general to more specific going down. Okay. So we can diagram this out with a dependency graph as to what depends on what here. But fundamentally, we're having that encoded within the makefile here. Okay. Okay. So basic action here is any dependencies of the sums of targets. They are automatically made, and the timestamp is the key thing to determine if something is out of date. Okay. Anyone know in Unix how to update something's timestamp without just overwriting it? Touch. You say touch X, and it will update X's timestamp. So sometimes in makefiles you'll see touches in there, just to kind of force it to update the timestamp of something so other rules get run. Okay. So the make command, we've seen the syntax, we're using it there. We have make minus f, the name of the makefile. By default, if you don't say minus f, makefile something or other, it will look for a makefile successively with different capitalization, and then some target. I think it actually could be one or more targets here. Here, you know, we might, for example, want to clean up, and then we'll say, okay, we'll make the Queen's target. So we're going to clean up here. So I'm going to remove all .o files. Yeah. And now what I'm going to do is I'm going to go make that using the makefile we've just looked at. So there we go. All these things have been run. And if I do an ls now all the .o files are there, all those intermediate files, but Queens is also there. So if I say Queens, I can do a board of size 4. And this is a configuration in chess of size 4, where no queen can capture only the other queen. The dot is just an empty board piece. Q is the queens. So here we have sort of produced the queens, and it knows how to do that appropriately. Let's suppose that I went back and I said, I want to make it again. What would happen, do you think? Suppose I said I want to make this again. What should happen? Nothing. It says it's up to date. But let's suppose that I were to go frob something. So just to illustrate this, maybe I'll touch solver.h, okay? Now what should it do? Well, based on this graph here, if I've changed solver.h, what things should be done? Tell me what you think the makefile will now update. Okay, so it'll need to update. We're going to be trying to get queens. To get queens, it has to get all these things in order. To get this in order, to see if this is in order, it checks the dates here. This is out of date, so it compiles this. Similarly, it compiles queens.o, and then it will compile queens. Does that make sense to people? So let's see that. So there we go. And it compiled solver, compiled queens, and queens.cc, and then it linked them together in order to produce this output. This is the linking step. Don't be confused. The linker also uses G++, but here it's being used in its capacity as a linker to link up these .o files. It's not processing your C files. directly. It's processing these O files and outputting this program. Okay, so we can see that it can keep track of things. Let's take a look at some additional refinement that can be used. One very common target is, or one very common need is to actually clean up, to force it to build things totally from scratch. Ladies and gentlemen, the truth of the matter is that sometimes we're unsettled because we're not sure the program has really taken everything into account. And for one reason or another, we may not know with confidence that the dates of the files, times and dates are proper. Maybe they've been taken from a different machine where we think it may be off slightly. In any case, we want to do a clean slate. We want to build something from the ground up. Okay? And this is referred to as a situation where we want to do a make clean. So we want to clean up the situation entirely. So, for example, in Makefile 3 here, we can go see a situation where we've added a rule for make clean. So here's the make clean rule. Now you'll notice that this is most interesting. What does this rule basically say? Okay. What is its dependency? Under what conditions, if we say make clean, under what conditions will this run? Always. It doesn't depend on anything explicitly over here. So it will run. You'll recall earlier, if we looked at Makefile 1, with Makefile 1, queens, for example, depended on these things. So if one of them was more recent than queens itself, it would do the build here. With make clean, we're not imposing any constraints on when it runs. It automatically runs. It runs regardless of the status of other files. If we say make clean, it cleans things up for us. Here it's running rm-f to force sort of rm to delete these things. So here, we can do a make clean, and oops, excuse me. Why did I get that? Why did I get that? Correct. And so it's looking around, it's sort of casting around for a file called Makefile, and actually it doesn't even, in this case, find it either with a lowercase or uppercase. So I can specify Makefile 3, which is the one we were just looking at, and I could say Makefile 3 clean, and here it goes and applies that rule. It cleans things up, okay? You'll notice, incidentally, it's not only deleting the intermediate things, it's deleting the final program. Why might I want to do that? Yeah, exactly. Like, maybe I'm not sure where this one came from. I'm not sure. Maybe it could have gotten corrupted. So I want to clean that up, and then I might do a broader make. I might remake that, for example. So I might remake queens. Alternatively, I might do make clean, and then I will simply say make -3, and that's actually just executing the default rule. The default rule, which for Makefile 3 is up here as normal, up at the top, and you notice there's a rule called all. Okay, so that's my default rule. If I don't specify what particular target to build, it will default to all. And in this case, what's going on? Help me understand the semantics. So all queens test, nothing under it. What does that mean? Yeah. First one. The first is the default. In this case, it's good practice to put the more general ones up top, the ones that do more work, and in this case, put all up top. So, what's the semantics of that, though? What does required cleans, and then make as required test. So make sure those are up to date. Put another way, to make sure everything is up to date, all is up to date, I need to make sure cleans is up to date and test is up to date. So what do I have to, so if it's trying to do that, what does it next go to? Well, it goes to Queens. And the next rule down says to make sure Queens is up to date, first make sure state.o is up to date, and solver.o Queens is up to date. And then, see, for me, for Queens, am I more recent than those? Or if not, I have to build it myself using that rule. So all is a very, very common, that's a sort of time-honored name to use to build everything from scratch. To build everything within the system. We often will do a make clean first to sort of wipe away the stuff, and then make all, so everything is built totally from scratch. Make all says, hey, make everything. So suppose I were to do a make all right now. Well, suppose I were to say make all explicitly, what will happen? What will happen? So actually, it's nothing to be done for it. Why? Because it already, why? Because, ladies and gentlemen, Queens is up to date. It's more recent than state.o. It's more recent than solver.o. It's more recent than queens.o. Test is also up to date. Test depends on test state and test solver. Test state depends on these things. It's more up to date than them. Test solver is more up to date than these. So it has no work to do. It's done. And just to be clear, it's the same thing. It's the default rule in this case. Okay. Okay. So that works. We can have all. We can have a clean mechanism as we've just seen. The problem is that it's an imperfect solution. Kind of force fit it into things. We've had these rules, but the issue is that we're using words like clean. Sometimes they're referring to a file. Sometimes they're referring to sort of a more abstract concept, like making things clean. In this case, our rule for clean down here at the bottom, did that produce a thing called clean? No, it didn't. Clean was not produced here. There's no clean produced. Suppose we had a file called clean. What would happen? So I'm gonna create a file called clean. I'm gonna touch clean. Okay, and now you'll see there's a thing called clean here. What do you think's in it? How would I see what's in it? Well, I could cat it. You're not going to see much of interest. How if I want to see how big it is? Well, I could grep for clean here. Okay, or I could just ls minus l clean. Okay, it's a size 0 length. How if I did file on it and see what it says? Okay, it says it's empty. Yeah. So there ain't nothing there. But is updated. So now what if I said make clean? What do you think will happen? Is that what I want? No. Not what your parents said. Clean up your room. Clean is up to date. I touch it. Well, yeah.
I guess if you really have something like a clean dot, see how we have to
Yeah. So you could work around it. It turns out that there's a more principled way of doing it. So there's no question there's workaround. And the point here is there's kind of this awkward abuse of, we call it, or awkward, this awkward sort of overloading of, it's another term we use in computer science. The word clean in our make file happens to be a legitimate file name. That could be a file name called all. Maybe it means automatic link locator or something like that. And we don't want to have to get that confused with when we say make all, that it gets puzzled by the meaning of that. So it turns out that Makefiles provide a way to deal with this. And this is getting a little bit closer to the Arcana, but you should be aware that quite common in Makefiles you see these things called .phony declarations. Okay, so targets that don't generate a file, they don't actually produce a real file, can be declared .phony. So clean, for example, is one of them. Or they have the same name as a file directory in your source tree, you can declare it .phony. And so if you look at the later, so just to be clear here, .phony tells Make the rule doesn't actually generate a file here. So it won't actually look. This is the key thing, folks. You can have a file called that, but it won't actually look to see if it's there. So let's take a look at Makefile 4, for example. Here we have a situation where we have a .phony, which is in here. So you'll notice that .phony is declared here up at the top, and it basically says, hey, look, if you're dealing with all, if you're dealing with tests, if you're dealing with clean, those are designations of actions that you want done, but they shouldn't be interpreted as names of a file. So you don't get this thing where it says clean is up to date, which may be true, but that's not what you're getting at. You want it to clean up, and it's just sitting there, saying this thing which is beside the point. So here we have this declaration which sort of states up front what are the different targets that aren't really files. They're more actions or commands that we give it. Okay, and you would do that for things that might be directories as well. Okay, so .phony rules will allow you to prevent these automatic remakes. So Makefiles, you're going to be seeing them, for lab today. You'll go, if you go out there and you look and you download things on Linux, for example, you download projects that have to be made, you'll find that Makefiles can become very large and very hairy. Okay, I've worked with Makefiles, which are at least many hundreds of rules, and possibly many thousands of rules. And as you appreciate here, it's recursive. It captures dependencies. It's designed to capture dependencies. And in a decent-sized project, you take it something like large pieces of Linux or what have you. This sort of diagram, which we had here, where is it? Which we had here, maybe many layers in depth, maybe tens of layers in depth, and you may have hundreds, if not thousands, of files included in this. So a Makefile, the job it performs is absolutely essential to avoid outdated files and therefore mistakes, situations where we're chasing phantom bugs. Bugs that aren't real bugs, they're just artifacts of the fact that we forgot to, after we changed this .h file, we forgot to kind of clean up after that and produce new versions of a set of things. The problem is that Make eventually gets bogged down, and it does become a quite arcane thing. So there's people within these larger C projects who specialize in Make scripts. And it turns out I'm not talking with you about a whole lot of things in Make scripts. I'm not talking about variables in Make scripts, for example. I'm not talking with you about certain types of macro-type mechanisms similar to C preprocessor macros. And the occurrence of those sort of things makes the situation very messy. If you go look at your Makefile 6, what you will find is a situation where we're actually making use of some of these mechanisms. So instead of listing things out, for example, here for each rule separately, so the fact that Queens depends on, state.l, solver.l, Queens.l, instead we can give names to things in sort of a C shell type syntax. So we can say Queens.object equals names. Why might we do that? In a big file, why might we create that sort of variable up there? Yeah, it's easier, it's more readable, particularly if you, and this is, I think, the other point that was being made, this may be used for many different places, and many different rules. Imagine a file hundreds of lines long, thousands of lines long, referring in many places to these three files. Well, there's a semantics associated. There's a reason it's those three files. It's because they're the objects associated with the Queens program specifically. And again, in a large project, you might have many different programs that are being built, all describing the same makefile. So some would relate to Queens, some would relate to other particular programs. So you can group all these things here, and then you just have to change it in one place. You don't have to worry about making it consistent, defining all the cases, and reasoning through, does it affect this one, does it affect that one? Instead, you just refer to these as all the object files in which Queens depends, and then you might do several different places. You'll notice there's some other condensation that goes on with these files as well. You'll notice that there's a curious absence of actual update mechanism of actions associated with these sort of dependencies. So here it says state that, oh, what is it dependent on? Means that, oh, it depends on these things. Where's the actual mechanism that's used? Where's the action component of it? Well, it turns out that this can all be defined up at the top. And we can actually define and say, okay, our C compiler is such and such. In this case, it's a C++ compiler. It has these certain flags to it, etc. And it actually knows, okay, this is a .o file. It depends on a CC file. And a CC file will make use of this certain type of compiler as indicated by this macro here. So you should be aware that makefiles can have these variables in them. They can become more dense, more condensed, more terse, and that allows you to sort of express things in a quicker fashion. At the same time, there's more moving parts. There's more mechanisms. You've got to look to more pieces of it to figure out things. So, up here you have all these sort of built-in mechanisms that are kind of known. Okay, for C files, you deal with this. For loading, in other words, for linking, the load time, link time operations, these are the flags to pass to the linker. You can define them in a single place. Why might you do that? Well, rather than defining that same set, of options here, minus WAll, minus WExtra, minus O3, you'll notice it's just repeated over and over again. If we wanted to update that, maybe to have minus pedantic or what have you, we'd have to do it at many places. We can consolidate that here up in one place at the cost of these additional mechanisms, at the cost of realizing that this stuff depends on these sort of variables. And in the sense that there's a little bit of magic going on, that there's a little bit of external mechanism. You'll notice that the types of mechanisms that are used within the shell scripts sort of encode these. It's a similar sort of style of defining these variables that you see out in the shell. So it's sort of influenced by a lot of Unix philosophy. So this is a makefile that exhibits some more advanced characteristics. What you'll be asked to do in your labs is quite simple compared to this sort of mechanism. It's a much more simple, basic use with the lower numbers. But all these files are on the Moodle site for you to inspect and learn from in support of your labs. Okay? So I think that's all we have time for today. I'll be talking next time some about the test-driven development process. We'll be using the Queen's example to go through successive versions